Welcome back, Design Junkies, to Mechanical Engineering Made Simple. Today we are moving beyond the simple one-dimensional analysis. We're sort of taking the safety goggles off and diving into the real world, a world where structural members rarely fail because of just one single mode of stress acting alone.
Exactly. For too long, foundational mechanics teaches us to solve for pure tension, pure bending, or pure compression.
Mhm.
But in reality, members often face all of these at the same time. Our mission today is to look at structural integrity through two critical integrated lenses. First, the concept of combined stresses, which really determines a member's ultimate strength. And second, a deep analysis of beam deflection, which governs its critical performance, or you could say, its stiffness. We've pulled from foundational mechanics texts, focusing on how we calculate the resultant behavior when members are subjected to both axial forces, that's thrust or pull, and bending moments simultaneously. We're giving you the shortcut.
Okay, let's unpack this combined stress situation first because it's incredibly common. Think of a short, stocky column or strut in a building. It's primarily holding up weight, which is a big axial compressive load, P, but maybe it's not loaded perfectly in the center, or, perhaps there's persistent wind pushing on it, inducing a bending moment, M. You just can't analyze the effect of P and M in isolation.
Right. If you try to treat them separately, the math is simple, but it's wrong. P acts down the center, causing uniform compression. M causes that gradient of stress tension on one side, compression on the other. But when they combine, the resultant longitudinal stress, which we call sigma, is the algebraic sum of the two stresses acting at any given point across the cross-section.
So if we look at the direct stress from P alone, that's purely compressive, uniformly distributed, and it's equal to the load P divided by the area A. That's the baseline.
Correct. The safety net, as you said. And if M acts alone, you get the familiar bending stress formula. M multiplied by Y, which is the distance from the centroid, all divided by I sub X, the second moment of area. And that stress is what creates the tension and compression symmetrically around the neutral axis.
Okay, so here is where it gets interesting and a bit algebraic. When you add them together, the resultant stress, sigma, is negative P over A plus or minus my over I sub X. We use the negative sign on that first term because by convention, compression is negative, so that P over A is constantly trying to keep the whole section pushed together.
And this combination leads to really two major outcomes for the internal stress distribution. In the first and most desirable case, the direct compressive stress, that P over A component, is so large that it just overpowers the tensile part of the bending stress. This means the entire cross-section remains compressive, which is ideal for materials
Like concrete.
exactly like concrete.
But what if that bending moment M starts to dominate the equation? Maybe because P is smaller or the beam is more slender.
Then you get the second, more dangerous outcome. The stress on one side of the member can become zero, or even worse, it can become tensile. The engineering consequence here is huge. It means the neutral axis, that line of zero strain, is no longer at the physical center of the beam. It's been pushed, maybe even outside the section entirely, or it's migrated way closer to the side with the highest compression. It just shows how much the bending moment has distorted everything.
That immediately makes me think of eccentric thrust, because sometimes the bending moment isn't from a separate force like wind, but from the load P itself not being applied right down the middle. So what if P is applied at a distance, let's say E sub Y, from the centroid C?
That is a beautiful mathematical simplification. That eccentric load P is statically equivalent to two things happening at once. It's an axial thrust P plus an induced bending moment M that equals P multiplied by E sub Y.
So we don't need a new set of equations.
Not at all. We just use the combined stress equation we just talked about, and we substitute P E sub Y in for M.
It's elegant. This leads to one of the most critical insights for civil and mechanical engineers. We know materials like masonry, stone, or unreinforced concrete are, well, they're terrible in tension. So if we need to prevent tensile stress from developing at all, there must be some kind of spatial limit on this eccentricity on E sub Y.
Exactly. We need to prevent the bending stress component from ever overcoming the direct compressive stress. For a simple rectangular cross-section with depth h, you can completely avoid tensile stresses only if that eccentricity E sub Y is less than or equal to h divided by 6.
H divided by 6. That sounds like a tiny sliver right in the center. Is that really where the load has to stay?
That region is formally defined as the core of the section. If the applied load P stays strictly within this core, the resulting combined stress guarantees that the entire section stays under compression. But if you let that load step outside that boundary, even slightly, you will inevitably induce tensile stresses somewhere in the member. and that leads to microcracking and eventual failure.
And the geometry of this core, it changes dramatically depending on the member shape, right?
It does, and it really highlights the challenge of geometric design. For that rectangular section, the core is a diamond shape or a parallelogram with diagonals of h divided by 3 and b divided by 3. But if you have a circular cross-section, common in piles or chimneys with radius r, the core shrinks even further. It's a small circle with a radius of just r divided by 4.
R divided by 4. I mean, that means in a column that's a meter wide, your load has to stay within a 12.5 centimeter radius of the center. That is a tight constraint, especially when you factor in construction tolerances or dynamic loads.
It's the non-negotiable safe zone. And to give you a feel for the magnitude, one of our sources ran a problem on a massive masonry pier 3 meters by 2 meters, subjected to 1,000 kilonewtons. Even with what seemed like minor eccentricities, the resulting calculations showed a maximum tensile stress of 0.008 meganewtons per square meter.
That sounds small, but in concrete or masonry, 0.008 meganewtons per square meter of tension is basically a crack forming.
Precisely. And at the same time, the maximum compressive stress was only negative 0.342 meganewtons per square meter. So the data confirms it. In materials with basically no tensile capacity, even a tiny deviation from true axial loading can start a failure because that slight eccentricity will pull the load outside the core and induce tension.
Which brings us to a really revolutionary application of this, prestressed concrete. Since concrete is so notoriously weak in tension, how does prestressing use this analysis to essentially, I guess, trick the material into behaving better?
Prestressed concrete is engineering genius, and it's based directly on that combined stress equation. You apply a massive, permanent axial precompression force, P, to the beam. It just acts as a constant, uniform, compressive floor. This precompression counters the tensile stresses that the eventual surface bending moment, M, would naturally induce. You're building in a permanent compressive buffer.
Wait, if we're trying to avoid tension entirely, why not just use that simple axial precompression every time? Why bother with the incredible complexity of eccentric precompression?
That's a great question. And it's all about optimization and efficiency. Simple axial compression is inefficient. It wastes compressive force on the top fibers, which will get compressed by the surface load M anyway. Eccentric precompression is the superior solution because it custom tailors the internal stress state before the surface load even arrives.
How does that tailoring work exactly?
Well, if you apply the precompression thrust P on the edge of the core, specifically at that h divided by 6 location below the center line, you create a very specific internal stress state before any surface load is applied. Because P is acting right at the boundary of the core, the upper fibers are at near zero stress, while the lower fibers are at a maximum high compression, specifically 2P over A.
So you're preemptively strengthening the exact region where the future tensile stress will hit the hardest, and you're leaving the top fibers neutral.
Precisely. So when the structure's own weight and external surface loads induce a typical sagging moment, M, that moment, tries to pull the bottom fibers into tension and push the top into compression.
Yeah.
But because we preloaded the bottom fibers with all that compression, we can perfectly balance the resultant stress. We keep all stresses safely within the concrete's allowed compressive limit and ensure zero tensile stress. Anyway,
It's incredible. So what's the bottom line difference in performance between the two methods?
the key insight is that precompression by an eccentric load gives a considerably higher bending strength than simple axial precompression.
Considerably higher.
In one comparison, the eccentric method allowed for nearly double the maximum allowable bending moment. It moves pre-stressing from just being a safe solution to an incredibly efficient one.
That really wraps up the strength side of the equation, the internal stresses, the material limits. But as engineers, we know strength isn't enough. We also have to ensure stiffness so the beam doesn't deflect too much and, fail functionally. So now we need to pivot and study deformation.
That's the critical link. The link between internal stress capacity and external performance. To analyze stiffness, we have to rely on the fundamental governing equation for the elastic bending of straight beams. It's EI multiplied by the second derivative of V with respect to Z squared equals negative M.
Okay, let's clarify those variables for a second. M is the bending moment, Z is the distance along the beam, and VV is the vertical displacement or deflection. That's what we're trying to minimize.
In that product, E times I is the most important measure here. It's the product of Young's modulus, E the material stiffness, and the second moment of area, I the geometry's contribution. This EI product is what we call the beam's flexural stiffness. Think of it as the beam's inherent resistance to bending. If you double I or E, you double the stiffness.
And by integrating this governing equation twice, we get those quick reference formulas that every structural engineer keeps handy, the fast checks. For example, a simply supported beam with a uniform load W spread across it. The max deflection V is 5WL to the fourth divided by 384 EI.
That exponent on L is what's terrifying for designers. Since the length is raised to the fourth power, even a small increase in the span lengths just crushes the stiffness. The source material showed a 6-meter beam with a 10 kilonewtons per meter load. Its max deflection was calculated to be 0.00844 meters.
Sounds small, but if your design limit is, say, 1/50th of the span, that number is critical.
And for a cantilever beam, the classic balcony or shelf with a concentrated load W on the end, the max deflection is WL cubed divided by 3 EI. Again, that length cubed means cantilevers are highly sensitive to length changes.
Okay, so direct integration works beautifully for those simple cases. But the real world often involves complex loading, a mix of distributed loads, multiple point loads, moments applied at odd points.
Right, and analyzing those individually means breaking the beam into a dozen separate segments. It leads to endless simultaneous equations to solve for all the constants. It's a mess.
That's where the elegant mathematical solution comes in, Macaulay's method. Anyone who's tried to solve a complex deflection problem late on a Friday knows just how powerful this technique is.
It really is a brilliant bit of algebra. Macaulay's method lets you write a single, continuous bending moment equation that's valid for the entire beam length, no matter how many point loads or moment changes you have. It just eliminates the need for all that separate, segmented analysis.
The trick is that famous Macaulay bracket, right? It's written like open bracket z minus a close bracket to the power n. When you integrate, you treat the expression inside those brackets just like any other term. But here's the clever bit. If the term inside the bracket becomes negative, which means the section you're analyzing is before the load at distance a, you just algebraically ignore that entire term. You set it to 0.
Think of that Macaulay bracket as a gate or a software switch. The equation is running down the beam, but the switch stays off, contributing nothing until you physically get to the point where that specific load W at distance A starts to have an effect. Once you pass A, the switch flips on, and that force gets integrated as normal.
It's a systematic approach that just simplifies everything. It minimizes the number of arbitrary constants and gives you one continuous equation for both slope and deflection across the whole structure.
But we have to move beyond the ideal. The real world doesn't always give us uniform cross-sections. What happens when I, the second moment of area, changes along the length? It happens a lot in weight-optimized or tapered designs.
So if I isn't constant, that EI term becomes a function of z.
Exactly. So in that case, EI is no longer a constant you can pull out of the integral. The differential equation now requires you to integrate the ratio of m over I along the length, instead of just integrating m. This is vital for, say, columns or beams designed for specific nonlinear performance.
One design application in the sources showed just how precise this can get. It was a cantilever strip with constant breadth, but a variable thickness, T, designed to bend into a perfect circular arc, which implies constant curvature along its length.
And to get that constant curvature, the second moment of area, I, had to be proportional to z, the distance from the free end. Since I is proportional to the thickness cubed T cubed, this meant the thickness T itself had to vary, so that T cubed was proportional to z. It's a stunning example of tailoring material based on a deflection requirement.
And finally, we've focused almost entirely on bending deflection. We've assumed that almost all the vertical displacement comes from the moment m. But we can't forget about shearing deflection. Does that truly matter in the big picture?
It depends entirely on the geometry, but yes, it can matter significantly. All those previous calculations assumed the shear force had a negligible impact on deformation, and that holds true for long, slender beams. But shear stress also causes its own lateral deformation. The shear strain, gamma, is proportional to the shear stress at the neutral axis divided by the shearing modulus G. This causes additional vertical deflection.
So when does this shear deflection stop being negligible? When do we have to worry about it?
The ratio becomes significant for deep beams, where the ratio of depth, h to length L, is large. If a beam is short and squat, the shear forces have a much stronger influence on the overall shape change than the bending moment does.
There was a specific data point from one of the design problems that should, I think, shock every engineer listening. It was a timber beam carrying a concentrated load. When they analyzed it, the total shear deflection was calculated to be nearly 30% of the total bending deflection.
30%. That is an enormous amount of unaccounted displacement. It proves that depending on the material, especially softer materials like timber and the geometry, neglecting shear can lead to seriously underestimating the total displacement. If you ignore that 30%, you have fundamentally jeopardized the required stiffness and performance of the structure.
That was quite a journey today. We started by tackling internal strength, understanding how compression and bending combine, defining that non-negotiable region, the core of the section, to avoid tension. Then we moved into calculating structural performance using flexural stiffness, EI, and using powerful tools like Macaulay's method to manage complex deflection equations.
And we learned that strength isn't just about the maximum stress, it's also about setting up a favorable stress state, like we saw with the shear optimization of eccentric pre-stressing. It's an elegant application of combined stress theory that nearly doubles the bending capacity for the same material.
So, as you move forward and apply this knowledge, here's a final provocative thought for you to explore. We found that the core of a circular section is r divided by 4. That limit is critical for static structures, but it becomes exponentially more important for dynamic ones. So how does understanding this limiting geometry influence modern design standards for things like concrete piles or, say, tall, slender structures like chimney stacks that are constantly subjected to swaying forces from acceleration or high wind? That r divided by 4 limit is the key boundary that dictates whether the entire structure stays in safe compression or begins to tear itself apart with tension. Always more to learn.
Thanks for diving deep with us.